Let's leave that there. So some things to keep in mind. We're talking about radiation. I introduced this idea that like radiation could be emitted or reflected in different directions. So let's consider this surface that I've drawn up here. And what I want to look at is you've got these 5 different rays that are being emitted. There's a special characteristic of a surface. If you take the probability, so I'm going to write P for probability, and let's call this ray A vector. So if I look at the probability of A, the probability of B, C, D, and E, and so on, right? I've got these 5. So the probability of each of these. If it turns out, so you can't read that, but I've just drawn probability of each of them. If it turns out that the probability that A is the direction is equal to the probability that B is the direction, and so on, then we have what's called a diffuse surface. All right, the natural intuition that you maybe get from a diffuse surface is, again, thinking about what you can see in front of us. So if I look at this wall, or you look at this wall, you're not seeing that there's like an image of yourself coming back at you, right? It's not a mirror. It's the opposite of a mirror. You see this sort of, well-mixed, uniform kind of light that's coming off of it. That's an indication that it doesn't really matter the direction. That is, that the direction doesn't have a preference when it's leaving. Whereas if you look at a mirror, or you look at some other surface where there's a really strong preference for direction, then it's sort of obvious that like where you perceive that, where you are when you perceive the light coming from that, it is really affected by the surface. So what we're going to assume in our modeling of surfaces is diffuse surfaces almost entirely. Right? You can get into non-diffuse optics. So if you think you want to get into like understanding how cameras or telescopes work, or you want to look at concentrating solar or these different applications, then you start to care about radiation in a specular way. That is a way where you care a lot about the direction of light. For our purposes, we only want to treat it as diffuse. All right. In other words, we're going to say radiation is fully independent of direction, right, for our purposes. All right, I want to give you maybe like some kind of an understanding of this other aspect that we're going to talk about, which is the spectral dependence. So we have the direction dependence. We're going to say there's none. We're going to have spectral dependence. What is, get some intuition about the spectral dependence of light. So if a surface is emitting light, it can do so at any frequency. Like it's not like the sun emits all at one frequency, right? It emits a spectrum, which is why we can see and perceive color, which is why we have ultraviolet and infrared. But this spectrum covers way beyond, say, what the sun can emit. So we just start at looking at this spectral dependence chart. What I'm showing is wavelength in micron. So anywhere from 10 to the minus 8th all the way up to 10 to the 10th wavelength. I just want to give you kind of an idea of where stuff falls on this. So if we looked at solar radiation, that's going to be kind of in this, this range here. So right about here, this is solar. So the solar radiation, everything that's emitted from the sun, or like 99.9% of what's emitted from the sun, falls in that range. So you immediately get the sense that there's sort of a lot more out there, right? Well, some other stuff that we might care about would be rays that, if they hit you, would cause significant damage. So that would be things like gamma and cosmic rays. So you can maybe chart out something like this. So we call this gamma and cosmic. Right, these are very, very high energy rays. Right, you're looking at very low wavelength. These are rays that are like left over from the formation of stars and the creation of the universe, the Big Bang, right? The big energy stuff that's happened has this stuff, and they're just sort of shooting around, right? So normally those are absorbed by our atmosphere, which is why we don't die all the time, which is great. So that's like the really high energy stuff. If you go up a little bit, now you're going to be looking at things like in this range, let's say here to right around here. So this might be X-rays. Right, so this is stuff you can be exposed to, but you don't want to be exposed to too much because it can cause problems. So X-rays in that region. We could flip around and go to the other side. So thermal radiation, let's say thermal radiation is about from here to here, thermal. And what do I mean by thermal? Well, all of this is actually thermal radiation, if you're going to be pedantic. All of this has energy associated with it. When we're talking about thermal radiation, we're sort of talking about, well, what is the stuff that normally exists in our world and the things that we care about and causes radiation exchange to be a significant factor, right? So thermal radiation is basically, this is the band of stuff that we care about as engineers in that range. We could do some other stuff. So like down here, maybe from 10 to the 4th up to roughly 10 to the 10th. This would be like radio, TV for those doing stuff over the air, radar, right, this range over here. So you can break things down pretty much into these 3 segments. On the very far left, the high energy stuff, right? This is stuff that you really very energy intensive. There's the middle, that's kind of where we exist. And then there's the right, which is more like used for information, right? And there's a reason why it's used for, it has such a long wavelength it can pass through stuff without too many problems. So that's why you end up using the stuff on long wavelength for information. Any questions on this? Okay. By the way, in the solar spectrum, we talk about like the visible part of this. Let me just show this in here. So it's about, where are we? Visible, right here. It's about like this. Right, so we can actually see that green bit. That's it. Kind of interesting.